So in this video we're going to have a look at how uniform convergence works nicely with integration, and of course we're going to do this with Riemann integration because we haven't yet seen Lebesgue integration. So this is the theorem then that we're going to prove in this video. In short, it's that if you have a sequence of integrable functions which converge uniformly to a limit function, then that limit function is going to be integrable as well, and the value of its integral is going to be the limit of the integrals of your sequence of functions. Saying it more fully, if we have our sequence of functions fn, and they're all defined over a closed interval ab and they're real valued functions, and let's suppose that every single one of the functions in this sequence of functions is integrable over the interval ab. Now let's suppose that the sequence of functions converges to a limit, and we'll call that limit f, and let's say that it converges uniformly to that limit. So not mere pointwise convergence, we have the stronger form of convergence, uniform convergence, and you do need that stronger form of convergence in order to conclude what we're about to conclude. You can conclude from the fact that all of the functions in the sequence are integrable that the limit f must be integrable over the interval ab, and more, you can say that the value of the integral of the uniform limit, so the integral from a to b of f dx, this is actually going to be the limit of the sequence of integrals. So each one of the functions in the sequence of functions, you can integrate it from a to b. That's what we've got here, the integral from a to b of fn dx. This will be some real number in each case, and then you can form a sequence of real numbers, which is the sequence of all the integral values. And then you can take the limit of that sequence of functions, and part of what we're going to prove is that that limit will exist, and its value will equal the value of the integral of your limit function. So this is very nice. It says that integration is playing nicely with uniform convergence. This very nice theorem that we would love to be true is indeed true in the case where we have uniform convergence. And in fact, the first thing I'm going to do is show that this doesn't hold true if you take away the uniform convergence. If you have only pointwise convergence and not uniform convergence, then you can find a counterexample where this doesn't hold true, where in fact you can have a sequence of integrable functions that converge pointwise to a limit function that is not integrable. And in fact, I can show you how it can break in two different ways if you take away the uniform convergence. So I can do one example, as I've just said, where we have a sequence of integrable functions where it converges to something that's not integrable. And I can come up with another example where you have a sequence of integrable functions that does converge to something that's integrable, but actually it's this bit that then breaks. When you look at what the value of the integral of the limit is, it is not what the limit of the sequence of integrals is. So I can come up with examples that break this theorem into two different bits if I take away the uniform convergence criterion and just have pointwise convergence and not uniform convergence. So this beautiful theorem only holds true when we have the stronger form of convergence, uniform convergence. So the first type of counterexample then, a sequence of integrable functions that converges pointwise to something that's not integrable. So the way that we're going to do this is we're going to find a sequence of functions that converges to the Dirichlet function. So I'll just remind you what the Dirichlet function is. It's an indicator function for the rational numbers on the interval 0, 1. So defined on the interval 0, 1, real value function, and this is how it's defined. So for all the numbers in the interval that aren't rational, it's mapped onto 0, and for all the numbers that are rational, it's mapped onto 1. So it's a complicated function to draw, because the uncountably infinite number of non-rationals in this interval are all mapped onto 0, but then the countably infinite number of rationals are all mapped onto 1. So it's kind of almost got two lines, a line here and a line here, and there's, in some sense, far fewer points up here being mapped up here than there are being mapped down here. Now the Dirichlet function is not Riemann integrable, and it's easy to understand why. If you imagine taking any partition you like of this interval 0, 1, and I've just drawn an example one on here, then in each one of these subintervals of your partition, there will always be a rational number and there will always be an irrational number, because the rationals and the irrationals are both dense in the real numbers, and therefore the supremum of the values of the function over each one of the subintervals, no matter how tiny the subinterval is, will always be 1, and the infimum will always be 0. Therefore, no matter what partition you take, the value of the upper Riemann sum for that partition and the lower Riemann sum for that partition are always going to be the same thing, because all you're going to do is take all of the lengths of the subintervals, and for the upper sum you're going to end up multiplying each one by 1, and for the lower Riemann sum you're going to end up multiplying each one by 0, because, as I say, for every single subinterval, no matter how small it is, the supremum of the values of the function over that subinterval will always be 1, and the infimum will always be 0, because of the fact that the rationals and irrationals are both dense in the real numbers. And therefore, when you tot up the sum, you'll get that the upper Riemann sum for your function over whatever partition you take is always going to be 1, and the lower Riemann sum for our Dirichlet function over any partition is always going to be 0. And that's whatever partition you take, and therefore the infimum of the upper Riemann sums is going to be 1, and the supremum of the lower Riemann sums is going to be 0, which are not the same, and therefore the function is not Riemann integrable. So now what I want to do is create a sequence of functions that are all integrable that converges pointwise to this Dirichlet function that is not integrable. So I can do this because of the fact that the rationals where this function is 1 is a countable set, and I have a countable number of functions in my sequence of functions. So this is how I'm going to do it. I'm going to start off with my first function in the sequence as just being the function that maps everything on the interval 0, 1 to 0. And then gradually I'm going to add more and more of the rationals in to being mapped onto what they need to be mapped onto for the Dirichlet function, which is 1. So my second function, f2 now, I'm going to firstly get it right at x is equal to 0. 0 is a rational, so it's going to be mapped onto 1. So I take 0 out of the collection of things that are being mapped onto 0. So now it's just x is an element of the open interval from 0 to 1, not including 0. They're all being mapped onto 0, but now 0 itself is going to be mapped onto 1. So I've made it correct at x is equal to 0 for the Dirichlet function. And then I continue on. I'm going to add in more and more rationals. So in my next one, I'm now going to make it correct also at the other end, which is 1. So I'm going to take 1 out of the things that are being mapped onto 0. So now it's x is an element of the open interval from 0 to 1. They're being mapped onto 0. But now x is equal to 0 and 1 are both being mapped onto 1. And now that means that all the things in the interval 0, 1 with denominator 1, all the rationals with denominator 1 are now being mapped onto the correct thing for the final Dirichlet function. So now I'm going to progress onto the rationals with denominator 2 that haven't already been included. So of course 0 and 1, you could view them as having denominator 2. 0 over 2 is 0 and 2 over 2 is 1, but they're already included because they can be expressed as a fraction with denominator 1. So now the only new rational with denominator 2 that I need to think about is x is equal to a half. So in the next one, I'm going to make it correct at 0, 1 and a half. So I'll take what I've already got, and now I'm going to make it correct at a half as well. So a half's now going to be mapped onto 1, and the things that are being mapped onto 0 is now x is an element of the open interval 0, 1, subtract a half, so not including a half now. And you'll continue on in this manner. So next you'll look at the rationals with denominator 3, and for your f5 function you'll want to make it correct at a third, so that a third is now being mapped onto 1 rather than 0, and then at f6 you'll want to make it correct at 2/3, so that 2/3 is now being mapped onto 1 and not 0, and then you'll have done the fractions with denominator 3, and then you'll move on to the fractions with denominator 4. So you'll want to get a quarter correct and 3/4 correct. You don't need to worry about half because we've already done that. And then you'll move on to the fractions with denominator 5. So you'll want a 1/5 to be mapped onto the correct thing, 2/5 to be mapped onto the correct thing, 3/5, 4/5, and you'll continue on in this way. And because of the fact that the rational numbers are countable, as you go on and on, if you give me any rational number, I can find a point in this sequence of functions where eventually at that point, at that function, and for all the functions afterwards, it will be being mapped onto the correct thing for the Dirichlet function, and that holds true for any rational, because the way that I'm doing it is so meticulous that every single one of them is guaranteed to be covered by it. So hopefully you can appreciate how this sequence of functions that I've defined, or at least told you how I'm going to build, is going to converge pointwise to the Dirichlet function. Just to talk you through why. So if we think about the limit as n approaches infinity of our sequence of functions, the pointwise definition is that you think of each point in the domain, so any x in the domain of which is the closed interval 0, 1, then the limit function is going to be the function that maps x onto the limit of the sequence of real numbers that you get by evaluating the sequence of functions at the point x. So now, if we think about what any irrational number is going to be mapped onto, so take an irrational x, then every single one of the functions in this sequence is always going to map an irrational number onto 0, because they are never going to be covered in this mechanism that I've described, which is converting numbers to being mapped onto 1, because it's only going to cover the rational numbers. So all the irrational numbers are always going to be mapped onto 0 by every single one of the functions in this sequence. And therefore, this sequence of real numbers that you get from evaluating the sequence of functions at x is just going to be the sequence 0, 0, 0, 0, 0 forever. And that sequence has a limit, and that limit is 0. So they're all going to be mapped onto 0 by the limit function. Good, so that's correct for the Dirichlet function. Now think about a rational number, so take x as a rational, then as I've said to you, whatever rational you give me, even if it's a really complicated one, at some point my mechanism will cover it. So I can go along, I might have to go a very, very long way along, but I can eventually get to one of these functions that will cover your rational and will make it be mapped onto 1. And then the way that I've defined this is then that all subsequent functions will include all of the points that the previous functions have mapped onto 1. So I can get to a point in this sequence where it and all the functions afterwards are mapping that rational onto a 1. And therefore, this sequence of real numbers, it may well start off with 0, 0, 0, 0, 0, so there may well be a long row of zeros in it, but eventually it will switch to being 1, and then afterwards it will remain 1 forevermore. And that sequence again has a limit, and that limit is 1. So that means that any rational number is going to be mapped onto 1 by my limit function. So, i.e., pointwise, this sequence of functions I've defined is converging to the definition of the Dirichlet function, where all irrationals are mapped onto 0 and all rationals are mapped onto 1. Now this sequence of functions that I've created, it doesn't converge uniformly to the Dirichlet function. It does converge pointwise as we've just discussed, but not uniformly, and I can show you that quite simply. So if you think about the criterion for uniform convergence and use epsilon is equal to a quarter, then what I've drawn here are the intervals around the limit function, the Dirichlet limit function here, of radius a quarter. So we've got these kind of tubes around this part up here, which is all the rationals being mapped onto 1, and then this bit down here where all the irrationals are being mapped onto 0. And if uniform convergence was being met, then there must be a term in my sequence of functions, an f big N, such that that term and all terms afterwards, but we don't need to worry about the all terms afterwards because it isn't even going to hold that there's one that's true, one function for which this is true. It would have to be the case that this function was within these blue tubes of the limit function for every single point in the interval. And that isn't going to ever be possible, because it would mean that every single one of the rational numbers in the interval 0, 1 was having to be mapped onto something within this tube here of 1. So i.e. between 3/4 and 1 1/4 up here. But that's not going to be the case, because for every single one of these functions that I've defined here in this sequence, or I've told you how I'm going to build in this sequence, there's always going to be some rational numbers that you haven't covered yet. So for this f big N, I'm always going to be able to find a rational number that hasn't been covered by it yet and is still being mapped onto 0 by it. And of course 0 is not between 3/4 and 1 1/4, and it needs to be in order for the uniform convergence criterion for epsilon equal quarter to be true, because by the limit function, the Dirichlet function, that rational will be being mapped onto 1. So now this function had better be mapping it somewhere between 3/4 and 1 1/4 in order for the uniform convergence criterion to be true. And that's just not the case. It's being mapped onto 0. And that's always true. No matter how far along you go in this sequence of functions, I will always be able to find your rational that you haven't covered yet, and therefore is going to break it being able to fulfill this criterion. So it may converge pointwise to the Dirichlet function, but it does not converge uniformly to the Dirichlet function. So I've got this sequence of functions that converges pointwise but not uniformly to the Dirichlet function, which I know is not integrable. So now all I need to do is show that all of the functions in my sequence, they are integrable, and then I'll have a sequence of integrable functions that converges pointwise but not uniformly to a non-integrable function. So I will have completed my first type of counterexample. So think now about all of these functions in this sequence. They're mainly the 0 function. So here I've drawn a picture. This is the domain, the interval 0, 1. And for nearly all of the points on the interval, they're going to be mapping them onto 0. It's just for a finite number of points that they're going to be mapping them onto 1. And yes, as you go further and further along in the sequence, that finite number of points is going to get bigger and bigger. But for each term of the sequence, so for each fn, whatever little n is, there will be a finite number of rationals that you have now corrected to being mapped onto 1. In particular, the way I've done this, f1 had no rationals, f2 had 1 rational, f3 had 2 rationals. So actually, the number of rationals that have been corrected for each one is going to be n minus 1. So there will be n minus 1 points that aren't being mapped onto 0 and are instead being mapped onto 1. So I want to now convince you that that function, where you've got a finite number of points being mapped onto 1 and everything else is being mapped onto 0 on this closed interval 0, 1, is Riemann integrable, and indeed that its integral is actually just 0. So let's consider a fixed term in the sequence, so fn. So we're going to fix the function that we're dealing with now, but our arguments will work for whichever one you choose to study. And let's firstly consider what the lower Riemann sum for this function fn for some partition is going to be, and I argue that it's going to be 0, and the reason is the same as what we saw with the Dirichlet function, where the lower Riemann sum over whatever partition you take is always 0. So if you imagine taking any partition, and I've drawn an example here, then in every single one of the subintervals there's always going to be an irrational, which is going to be being mapped onto 0, and therefore the infimum of the function over each one of the subintervals is going to be 0, and therefore when you take the lower sum, you're multiplying each one of the lengths of the subinterval by the infimum of the function over that subinterval, i.e. you're going to get a bunch of zeros being added together, and overall that will make 0. And that's going to be the same whatever partition you take. It's always going to work the same way. So all of the lower Riemann sums are going to be 0. Now let's think about the upper Riemann sums for our function fn for a partition P. Now this is obviously more complicated because it will depend on what partition you pick. So I've drawn another partition here in blue, and the aim of this partition is to show the little subintervals that are containing the points that are being mapped onto 1 rather than 0, of which we know there are finitely many. Now if you think about finding the upper Riemann sum, you're going to go along each one of these subintervals, you're going to multiply the length of the subinterval by the supremum of the function over that subinterval. Now if the subinterval doesn't contain a point that is being mapped onto 1, then everything will be being mapped onto 0, and therefore the supremum of the function over that subinterval will be 0, and therefore you'll get no contribution to the overall upper Riemann sum from that bit, because you'll have 0 times the length of the subinterval, which is 0. So that won't contribute at all. On the other hand, if you have a subinterval that does contain one of the finitely many points that is being mapped onto 1, then the supremum of the function will then be 1, and you'll get 1 times the length of the subinterval, so you will get a contribution to the upper Riemann sum. So in fact, hopefully you can see that the upper Riemann sum for a given partition is actually just going to end up as the sum of the lengths of all of the subintervals that happen to contain a point that is being mapped onto 1. So in this case, here is a subinterval, here is a subinterval, here is a subinterval, here is a subinterval. All of these subintervals contain one of these points that is being mapped onto 1. So actually all you need to do is take the length of this one, 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 and take the length of this one, and add those together, and that is going to be your upper Riemann sum. So I've tried to write that out here. It's the sum of the subintervals, the delta xi's, where you just want to take the subintervals that contain a point that is being mapped onto 1. So delta xi needs to have an element x inside it such that fn of x is equal to 1. Now, we know that there are finitely many points that are being mapped onto 1, so what you can do is make these subintervals that contain those finitely many points as small as you like. You can make them indefinitely small. They have to still contain that point that's being mapped onto 1, but you can make them really, really tiny, and therefore you can overall make this sum, which is going to be the value of the upper Riemann sum, as small as you like. And that means that if you think about, by changing the partition, so making a partition where the subintervals that contain the points that are being mapped onto 1 are smaller and smaller and smaller and smaller. So that means that if you think about all the values that the upper Riemann sums can take on, you can make it as indefinitely close to 0 as you like. So in fact, the infimum of the upper Riemann sums is also going to be 0. So the supremum of the lower Riemann sums is going to be 0, because all the lower Riemann sums are 0, and the infimum of the upper Riemann sums is going to be 0. Now, of course, none of the upper Riemann sums are actually going to be equal to 0. You can't ever get them equal to 0. You'll always have something here, but you can get it as indefinitely close to 0 as you like, and therefore when you think about the infimum of the set of all the values of the upper Riemann sums, it's going to be 0. So the supremum of the lower Riemann sums and the infimum of the upper Riemann sums are going to agree, and therefore the function is Riemann integrable, and the value of that integral is 0. And that is the same no matter which one of the functions that you go on to. This argument holds true for any n, because the number of points that you've got that are being mapped onto 1 is still finite, so this argument of you being able to make this as indefinitely small as you like is still going to hold true. So all of the functions in this sequence of functions are integrable, and they have integral value 0. So that then completes this first type of counterexample. I have found you a sequence of integrable functions that converges pointwise to this function that is not integrable. And so it's a first example of how, if you take away the uniform convergence and just have pointwise convergence, this lovely theorem does not hold true. We'll have a break here, and in the next video I'll give you another example of where this doesn't work if you take away the uniform convergence. But it's not the integrability that breaks. We can find an example where the limit is still integrable, but this bit breaks, where the value of the integral of the limit is not the limit of the value of the integrals.